Welcome everybody to Math 104. Today we're going to be working on sections R2 and R4, so a lot of review material here. Sets, exponents, roots, and order of operations. And you can see the objectives there on the packet. And on the first page we've got a bunch of vocabulary and symbols. And I'm not going to go over those initially, I'm just going to point them out as we see them in the lesson. So let's turn to page 2. And set builder notation. So set builder notation is a way of writing sets of numbers. A set can be anything in the real world. It could be a set of steak knives, a set of weights for your weight bench, and there's a million examples. But set builder notation is a way to write numbers. And we're going to be writing answers like solutions to equations in set builder notation. So it has a format of enclosing everything in curly braces, and then writing your variable name here. So let's say we start with an x or something like that, and then this line is read as such that. So we're talking about the variable x such that, and then we're going to have a list of requirements for x. Kind of narrows things down, because x could be any real number, and we want to narrow it down just to things like a solution set. So let's take a look at the first example. I've got list the elements in the set. This is x such that x is a natural number less than 8. So there's your requirement. It has to be a natural number, first of all, so there's one requirement, and less than 8. So two things we have to keep in mind when we're writing the set. So a natural number is the counting numbers. We're going to start at 1 and count up from there. 1, 2, 3, all the way to infinity. Those are the natural numbers. But we only want the ones less than 8. And by less than 8, I mean strictly less than 8, not including 8. If it meant 8 included, it would say less than or equal to 8. Alright, so if we list these numbers, it's 1, 2, 3, 4, 5, 6, and 7. So there's our list of numbers, all the natural numbers less than 8. And then we'll just enclose that in curly braces. And now we've got the answer in set notation. Now that brings us to your turn number 1. It's essential that you work on the your terms. Yeah. I'm just going to go ahead and write on and present the solution to your turn number 1. What you should do is pause the video, work on your turn number 1. Once you finish it, then resume. Alright, so your turn number 1. What we're talking about here are elements in the set x. X is a whole number less than 5. Now the difference between the whole numbers and the natural numbers is that the whole numbers include 0. So that's going to be 0, 1, 2, 3, and 4. So there's all the whole numbers less than 5. Alright, next up, we are given a question in set builder notation. List the elements of the set x such that x is a whole number greater than 5. Alright, whole number greater than 5, so we'll start at 6, 7, 8, 9, and it doesn't give us an upper limit. So this list is going to go on forever. So what we're going to do now is include the ellipses. And this is one of the symbols off the first page. And this means the pattern continues forever. Now there are some ways to use ellipses so that it's not the pattern that continues forever. If I, let's say, put a 10, I don't know, let's say a 20 here inside the braces, that means the pattern would continue on until you hit 20. But if you don't have a number following it, if it's just the ellipses, then it just goes on forever. So there's a difference then between this set and this set. In this one, we know it has 1, 2, 3, 4, 5, 6, 7 elements. This is called a finite set. There's a countable number of elements in the set. Over here, this is called an infinite set because we don't know, we can't say how many elements there are in a set because it goes on forever. Now, element is one of those vocabulary words. It means a member of the set. So let's say for this set here, I know that 4 is in the set, so 4 is an element of that set. So I could write something like 4 is an element of this set. And that's a true statement because 4 is in the set. That brings us to your turn, number 2. So pause the video here, go ahead and work on number 2. List the elements in the set such that x is a natural number greater than 2. So if it's greater than 2, that means we're going to start at 3. And on it goes forever. Just included enough numbers here to establish the pattern, and then we know it's every number that goes on forever from there. All right, next example, list the elements in the set x such that x is an integer multiple of 3. All right, now the integers are like the whole numbers, but they also include all the negatives. So this includes every whole number, positive and negative. Now the multiples are what you get when you multiply all the integers by 3. So that would be 3, 6, 9, 12, and so on. But it's also negative 3, negative 6, negative 9, negative 12, and so on. So it's every multiple of 3 in both directions. So to write this one, we're going to have to establish an infinite pattern in both ways. So we're going to have 2 sets of ellipses in this one. I included a few more numbers here than really is necessary. To give an example, I only go out through negative and positive 6. That's really enough to establish the pattern, because we can clearly see we're going by 3s, and you can include the ellipses after that. I just included a few more numbers just for demonstration purposes. All right, so that would be every integer multiple of 3. And that brings us to your turn, number 3. So with this one, we're listing the elements of the set x such that x is an even natural number. All right, going back to the definition of natural numbers, those are just the counting numbers. 1, 2, 3, and so on. So if we want the even natural numbers, that means we are going to start at 2. Skipping over all the odds, 2, 4, 6, 8, and that goes on forever. All right, last example, write the even elements of the set 1, 3, 5, 7, 9. All right, there are no even elements in that set, so the answer is the empty set. And the symbol for the empty set is a 0 with a line through it like that. And that's used to indicate that maybe an equation has no solution. In this case, it's to signify that there are no even elements in that set. All right, now we're going to start using set builder notation. So, next example, we're using set builder notation to write a description of the set 3, 6, 9, 12, and 15. A little space here. All right, so we wanted the description and set builder notation of this set. So we're going to start off with our variable name and the line. So x such that, and here we clearly have multiples of 3 because we're counting by 3. Now we're not talking about integers because we don't have any negative numbers. And we do not have 0, and 0 technically is a multiple of 3. It's 3 times 0. So that rules out the whole numbers. So the set has to be the natural numbers. So x is a natural number, and as said, x is a multiple of 3. And we stop at 15. So I'm just going to say x is less than 16. All right, so there's our comma-separated list of requirements. Sometimes you can do without the comma if you just say things all at once, kind of like that first example where x is a natural number less than 8. There are 2 requirements in there, but you don't need a comma because it all kind of flows. But you can write it like this as well. Now this is not the only way that this can be written. What we could do is say x is an integer, changes the integer, and then we'd have to add one more requirement where x is greater than 2 or something like that. So there's going to be multiple ways of writing this. This tends to be the most concise way of doing it. All right, that brings us to your turn number 4, looking for 3 different ways using set builder notation to write a description of the set 1, 3, 5, and 7. All right, so one way this can be done is call x an odd natural number. And that takes care of most of it, but this would be an infinite set, go on to infinity, so we have to cap it at 8. So we say x is less than 8. And it's okay to use symbols in set builder notation. You don't have to write it all out in words. And in fact, there are ways to write this in symbols. You don't have to do it this way, but you could say x is an element of the, there's a symbol for the natural numbers, and x is less than 8. So it's okay to write it out in words if you'd like, or you can use the symbols like this if you feel comfortable using these symbols. So this is read, x is an element of the naturals, x is less than 8. Next one, we could also do x is an odd whole number. And that's going to be the same set because even is technically, or 0 is technically even. So it would not be included in that set. So even though 0 is in the whole numbers and not in the natural numbers, it wouldn't be in the set because it's even. And then we still have to have x is less than 8. And then we could do x is, and it doesn't matter if we do a natural or whole here. So x is not a natural number, and x is less than or equal to 7. So since it's less than or equal to, it's going to include the number 7, and we get the same set that way. So any of those would work. So there's going to be multiple ways of writing these things. Our next topic is absolute value. The absolute value is distance from 0 on the number line. Now, distances are always going to be positive. So it doesn't matter which way we go from 0, we just count the number of moves, or the number of units. 1, 2, 3, 4, 5. If I go 5 to the left, I get to -5. If I go 5 to the right, I get to 5. These both are 5 away from 0, so the absolute value of both of those numbers is 5. So really, absolute value has the effect of stripping away any negatives. All right, now, when evaluating absolute values, you've got to consider order of operations. The absolute value bars are a grouping symbol. So in the order of operations, those are evaluated first. So always evaluate inside the absolute value bars first and then outside them. So for example, we've got the absolute value of -5 minus the absolute value of -2. Now you might look at this and say, okay, we've got a couple of negatives here. Generally when I'm subtracting, if I'm subtracting a negative, I can just turn it into a positive. Well, that works if this would be parentheses, but it's not, it's absolute value bars. So we have to evaluate it first, inside the absolute value bars. So this would be 5, absolute value of -5 is 5, and then we're going to subtract the absolute value of -2, which is 2. So now we just got 5 minus 2, or 3. All right, your turn, number 5. All right, so the absolute value of 7 is 7, plus the absolute value of 3 is 3, and that's 10. All right, next example. We've actually got an entire expression inside the absolute value bars. So we're going to do the negative of the absolute value of -5 minus 4. Again, we're not going to be canceling these negatives because we need to evaluate them one at a time. We're going to evaluate inside the absolute value bars first. So -5 minus 4 is -9. And this turns into negative of, the absolute value of -9 is 9. And then whenever you have a negative outside the number of parentheses, that's just -9. These two expressions are equivalent. Your turn, number 6. All right, so inside the absolute value bars first, you know 7 minus 3 is 4, so we got negative the absolute value of 4. Now the absolute value of 4 is just 4. So we get -4 for the answer. All right, next up, we're going to be ordering numbers less than or greater than. And we can look at the number line, see which numbers are going to be less than or greater than. We got smaller numbers this way and larger numbers this way. So anything that is to the left of something that's going to be smaller than things on the right. So we can look at a statement like -5 is greater than -3. And we're going to figure out whether or not it's true. Now, it may seem like this is true because the 5 is bigger than the 3. But when you have negatives, it's switched. Because -5 is to the left of -3. -5 is smaller than -3. So this is false. To make it true, you have to switch that around. Because with greater than or less than signs, the smaller side points to the smaller number. The bigger side points to the bigger number. That's a way to remember which one's less than or greater than. And next example, we got, now we're on your turn, number 7. So we'll see if this statement is true, -12 less than -8. -12 would be out here, so it's to the left of -8. So that is a true statement. All right, next one, we want to rewrite the statement to use the greater than sign instead. So what we need to do is flip the entire thing. We need to bring the 8 over to the left, flip the sign, and the -2 on the right. So it's still a true statement here. 8 is definitely greater than -2. And that brings us to your turn, number 8. Alright, so with this one, we are going to rewrite -9 is greater than -17 using less than instead. So switch everything around, 17 goes on the left, swap the symbol, you got less than, and -9. Alright, next topic is evaluating exponential expressions. So I'm sure you've all seen exponents before. Exponents just represent repeated multiplication. And we're going to look at a few specific examples where students tend to get a little tripped up on them. So the example we're starting with is what you do with an exponent on a fraction. So 4/5 to the 3rd power. Keep in mind, the exponent has to be applied to everything on the inside of the parentheses. So that means both numerator and denominator are going to be to the 3rd power. So you can rewrite this as 4 to the 3rd over 5 to the 3rd. Then we just evaluate the numerator and denominator separately. So 4 to the 3rd goes 64. 5 to the 3rd is 125. So 64 125ths. And that brings us to your turn, number 9. Just a reminder, make sure you're stopping the video, work out your turn, and then continue on. So here we've got 5/9 squared. So we'll apply the exponent to both the numerator and denominator. We got 5 squared over 9 squared, and that is 25/81. Now this is where I see the most mistakes. And that's when we start including some negative numbers. So there's two situations we need to compare and keep straight. So when we're multiplying negative numbers, every pair of negative numbers is going to have their negatives cancel. So if you have an even number of negatives, all of those negatives are going to cancel out. But if you had an odd number of negatives, you're going to have pairs of negatives that are canceling, but there's going to be one left over that doesn't have a partner. And that negative is going to stay in your answer. So if you're multiplying an odd number of negatives, you're going to get a negative answer. If you're multiplying an even number of negatives, you get a positive answer. So let's take that idea and compare what we get when we have negative 2 to the 4th power versus negative 2 in parentheses to the 4th power. These mean very different things. These are not equivalent to each other. This is a mistake I see quite often. What this means is we're taking 2 to the 4th power, so the base is just the 2. And when we're done taking 2 to the 4th power, through order of operations, we're starting with that exponent. When we're done with that, then we multiply by negative 1. So we're going to have a negative answer here, because what this equals is negative 1 times 2 times 2 times 2 times 2. That's the meaning of that expression. This expression means negative 2 times negative 2 times negative 2 times negative 2, because negative 2 is the base. The entire thing inside the parentheses is the base. We multiply this out, here's a pair, negatives cancel, here's a pair, negatives cancel, and we get 2, 4, 8, 16. And this one is negative 16. Your turn, number 10. All right, the first one is negative 6 is the base. 4 is the exponent, so we get 4 negative 6's multiplied there. The negatives all cancel, and we're left with 6 to the 4th power. And that is 1296. With this one, we have negative times 6 times 6 times 6 times 6. We got negative 1296. All right, square roots. Square roots are signified by the radical symbol. So what we're looking for is any number, when multiplied by itself, equals the number underneath the radical. That's what a square root is. So since 3 times 3 is 9, the square root of 9 is 3. And 9 actually has another square root, which would be the negative version, because negative 3 times negative 3 is also 9. So there's technically 2 roots to every square root, but the radical symbol itself only refers to the principal square root, and that is only the positive version. So when we're solving equations, we're gonna need both of the solutions. We're gonna need both the positive and the negative. But when we're just evaluating a square root, we'll just use the principal square root. All right, so let's take a look at three different versions of the similar square roots. We've got the square root of 49, we got the square root of negative 49, and we have this negative square root of 49. So square root of 49, it's the principal square root, only the positive version, so we'll just write down 7. Now this one is negative, so negative roots do not give us real answers, they give us complex answers, imaginary numbers, which we'll see later on in the course. But for right now, it's not a real number. All right, for this one, we'll evaluate the root first. So square root of 49 is 7, and then multiply by negative 1. So this one gives us negative 7. So make sure you keep those three situations straight. Your turn, number 11. I don't know if we can read that. All right, square root of 64, that's 8. Not a real number there. And this one is negative 8. All right, just like with exponents, if we're going to take the square root of fraction, we can take the square root of the numerator and the denominator separately. So the next example is square root of 9 over 36. So that is equal to the square root of 9 over the square root of 36. And the square root of 9 is 3. Square root of 36 is 6. And that reduces to 1/2. Your turn, number 12. All right, your turn, number 12. We have the square root of 121 over 4. So doing these two separately, you get the square root of 121 over the square root of 4. And square root of 121 is 11. Square root of 4 is 2, so 11 halves is the answer. All right, next topic is order of operations. So this is a way of making sure everyone gets the same answer when evaluating expressions. So order of operations starts with grouping symbols. So grouping symbols are like parentheses, absolute value bars, could be the division bar. The division bar meaning you work on the numerator and denominator separately. So things like that. Exponents are next. Then we'll do multiplication, division, working left to right. Finally, addition, subtraction, again, working left to right. So let's look at some examples of evaluating expressions using the order of operations. And this is, it's hard to pick a single most important topic in algebra. but if I was forced to, it might be order of operations, because it affects nearly every calculation we do with any expressions of any complexity. So example here is 4 times 6 minus 18 divided by 3. So we have no grouping symbols and there are no exponents. So we're moving right on to stage 3, multiplication, division, left to right. So the first thing we should do is multiply these two together. So 4 times 6 is 24, minus 18 divided by 3. All right, next up, we have another division, so we're still on step 3. I'm going to do this one. So 24 minus 18 divided by 3 is 6. And then finally, we have a subtraction left over, so we're on step 4, and we get 18. Now there are some shortcuts you can do. I did here in 2 steps what can really be done in 1 step. Because we're separated by subtraction, and doing this multiplication here and this division here, they don't affect each other. So technically I could have gone right from this step to this step, and I'd still get the right answer. So as you get more experience, you'll see when you can take shortcuts like that. And that's fine if you do that as well. Your turn, number 13. So for this one, I am going to use the shortcut. I'm going to do those first 2 steps at the same time. So we have multiplication, division, left to right. 24 divided by 3 is 8, plus 2 times 6 is 12, add them together, and we get 20. All right, next example. This is one. It's going to be helpful to compare this with the first example. So we got 12 divided by 6 times 2 plus 7. Now this one should be done 1 step at a time because these 2 operations are right next to each other and they will affect each other. If I were to multiply first, I'm going to get a much different answer. So I'll get 12 here. 12 divided by 12 is 1. 1 plus 7 is 8, which is not the correct answer. So instead of that, what I'm going to do is 12 divided by 6, that gives us 2. So multiplication, division, left to right, that's the first one we encounter, so that's the first one we do. All right, now I'm going to do 2 times 2, that gives us 4 plus 7. And then add those together to get 11. Your turn, number 14. Got 22 divided by 2 times 3 plus 4. All right, no grouping symbols or exponents. So we're going to move to stage 3, multiplication, division, left to right. So we'll do this division first. 22 divided by 2 is 11. Times 3 plus 4. So get in the habit of doing an operation, writing everything else down exactly as you see it. So we're not changing anything else. We're going to combine these 2. The 3 comes down, plus comes down, the 4 comes down. Next up, 11 times 3 is 33. Plus 4. Add those together, and you get 37. All right, next example, we're going to include some absolute value bars. Let's see if I have enough room here. Like so. All right, so in this one we do have some grouping symbols. So we'll start up here. Stage 1, the grouping symbols are the absolute value bars. I'm going to evaluate that first. Everything else is going to come down exactly as written. And then 2 minus 4 is negative 2. I still have to evaluate this thing. Still have the grouping symbols there, so I'm going to continue working inside there. And we have a 3 outside an absolute value. The implied operation here is multiplication. So whatever I get here, I'm going to multiply by 3. So I got 3 times the absolute value of negative 2, which is 2. Alright, so we've gotten rid of the grouping symbols now. No exponents. Can move on to multiplication division, left to right. So starting here, got a division. 16 divided by 4 is 4. Plus 3 times 2. You could use the shortcut there, but I'm just going to do it in 2 steps. So now we've got multiplication division here. So 4 plus 6. Now we're down to addition subtraction. And 10 is the answer for that one. Alright, we're on to your turn, number 15. So all sorts of stuff going on here. We have a grouping symbol, so we will start here. 18 plus negative 30, that's the same as 18 minus 30. 18 minus 30 is negative 12. So negative 12 goes inside there, and everything else will come straight down. All right, now I evaluate this. Absolute value of negative 12 is 12. So we got 12 divided by 2 minus 6 times negative 1. All right, now I'm going to use the shortcut. So 12 divided by 2 is 6, minus, and then 6 times negative 1. This is where it gets a little tricky because you got a couple of negatives in there. We're subtracting whatever we get from multiplying these two things. 6 times negative 1 is negative 6. So I'm going to put that in parentheses because you never want to put two operations in a row. You don't want to do minus, minus. If you're going to do that, it should be in parentheses. All right, now we're subtracting a negative. That turns into addition. So that's 6 plus 6, and that is 12. Now, next example, we've got a little bit of everything. Make sure you work your way up to the point where you can handle these larger, more complex expressions with all of the stages. All right, so we're going to start with grouping symbols. I've got a couple of them here. These won't affect each other if I operate on both of these at the same time. So I'm going to work inside both of them. Now, when we get inside a grouping symbol, we're just going to do the order of operations within the grouping symbol. So just within here, we've got subtraction and division. So we'll start with division, stage 3, inside the grouping symbol. Everything else is going to stay the same. So I'm going to bring the 9 down, the division, and then here we've got 12 minus 18 divided by 2 is 9. Close that. Minus 3 times 8 minus 10 is negative 2, and have that to the third power. Okay, here, one more thing I can do inside the grouping symbol, so I'm going to do that. 12 minus 9 is 3, so 9 divided by 3, and 3, and negative 2 to the third power. All right, now we simplified everything inside the grouping symbols. So now we can move on to stage 2, exponents. So we'll do negative 2 to the third power. Negative 2 to the third is negative 2 times negative 2 times negative 2, so that's an odd number of multiplications of a negative number. So that's going to be negative, so it's negative 8 there. So everything else stays the same. Going to bring down 9 divided by 3 minus 3 times negative 8. And well, now it looks like one of those first examples where we got a division, got a multiplication here, so I can do those at the same time. Do a 3 here, 9 divided by 3, minus, and then 3 times negative 8 is negative 24. So don't lose that negative. All right, now we're subtracting a negative, so 3 plus 24, and we get 27 as the answer. All right, next up is your turn, 16. So we've got grouping symbols. So I'm going to evaluate this. Within this grouping symbol, the order of operations tells us to start with the exponent. So I'm going to start there. So 15 divided by 30 minus 5 squared is 25. So just replace that with a 25. And then 18 minus 21 is negative 3. And when things get more complex like this, I recommend keeping things kind of in their lanes. Copy things down that you're not operating on directly below them. It helps to keep things organized. I can continue on here. 30 minus 25 is 5, so we get 15 divided by 5 plus 3 times negative 3 to the third power. And that completes simplifying within the grouping symbols. So now we're ready to move on to exponents. So 15 divided by 5 plus 3 times negative 3 to the third power. We have an odd number of negatives, so it's going to be negative. 3 to the third is 27, so that is negative 27. All right, now we've got a division and multiplication. So 15 divided by 5 is 3. 3 times 27 is 60. Negative 81. So 3 plus negative 81 is going to give us negative 78. Right now we can look at some fractions. And keep in mind what I said earlier about the division bar being a grouping symbol. So it separates the numerator and the denominator, and we can just work on the numerator and denominator separately, and then once we get a single number on top and a single number on the bottom, then we can simplify, and there's your answer. Next example, 33 minus 2 times negative 3 squared all over 2 minus 3 times negative 1. So order of operations on top, just looking at the numerator, we're going to start with the exponent. Negative 3 squared, the negatives are going to cancel, and that's just 9. So we got 33 minus 2 times 9. And down here, we got 2 minus 3 times negative 1 is negative 3. So it's 2 minus negative 3. Easy to lose one of those negatives, thinking maybe they cancel or something. Not yet. Make sure you keep that. All right, continuing on with order operations up top. Next one is multiplication. So we got 33 minus 18. And we can convert this to 2 plus 3. Subtracting a negative is adding. That's 2 plus 3. Okay, subtracting those, we get 15. And then 5 on the bottom. All right, now we're down to a single number on top and a single number on the bottom. And only then should you divide. 15 divided by 5, and we get 3. Your turn, number 17. Up top, we've got a multiplication and multiplication. We're separated by subtraction, so it's okay to do those at the same time on the same step. So we'll start left to right. We got 16 there, minus, and then 3 times negative 4 is negative 12. So put that in parentheses, 16 minus negative 12. And on the bottom, we're going to start with the grouping symbol, 25 minus 2. So that is 3. Minus negative 4 squared. All right, next up, you can convert this to addition or subtracting a negative, so that is the same as adding 16 plus 12. And the bottom, now we're at the exponent stage. Negative 4 squared is 16. It's going to be positive 16 here. So we've got 23 minus positive 16. And now we can finish up. You got 16 and 12 gives us 28 on top. And then 23 minus 16 is 7 on the bottom. All right, now we're down to a single number on top, single number on the bottom. Now we can finally divide. 28 divided by 7 is 4. And now last up, this is the same type of a problem, except we're going to be given variables, and then given the values of those variables, you just need to plug the values in. So this is a very common thing to have to do in applied mathematics, such as scientific applications. A lot of times you're just given a formula, say, okay, we got to do some experiment, we get all the values, and we take all the values and plug them into the formula, and then you can get some answer out of it. So we're going to evaluate an expression and that expression is 3d minus b over b minus 2c. And for both this example and your turn, we're going to be using these values over here. I'll write down a equals 2, b equals 3, c equals negative 1, and d equals negative 4. So these are the values we will plug in. When plugging values in, I highly recommend using parentheses. It's actually required if you're going to plug in negatives in a situation like this where you multiply. So 3 times negative 4 minus, and then b is 3. Down here we got a 3 minus 2, and then c is negative 1. So just make sure you put those values in parentheses. All right, we'll do order of operations on top. 3 times negative 4 is negative 12, and then minus 3 stays. And here we got 3 minus, and 2 times negative 1 is negative 2. So put that negative 2 in parentheses. All right, now we can evaluate the top. Negative 2 minus 3 is negative 15. And down here, we're going to convert this to addition. 3 minus negative 2 is the same as 3 plus 2, or 5. All right, we got a single number on top, single number on the bottom. Now we can divide. 15 divided by 5 is 3. Keep that negative. Answer is negative 3. Your turn, number 18. So let's plug in. Negative 3 times negative 4 divided by, and in parentheses, we got a times b, so that's 2 times 3, minus 4 times c, which is negative 1, put that in parentheses, 2 times b, so that's 2 times 3, plus c, and negative 1 again in parentheses. Order of operations. So work inside the parentheses first. So up top, 2 times 3 is 6. Minus 4 times negative 1 is negative 4. So 6 minus negative 4. And on the bottom, 2 times 3 is 6. Plus negative 1, that's the same as adding or subtracting a positive 1. So 6 minus 1 on the bottom. Continuing on, got negative 3 times negative 4 divided by, let's finish off inside the parentheses. Here we got 6 minus negative 4, that's the same as 6 plus 4, or 10. 6 minus 1 is 5. So negative 3 times negative 4 divided by 10 divided by 5 is 2. All right, now we're down to a single statement here. So we got negative 3 times negative 4 is 12. Positive 12, because negative times negative is positive. Divided by 2, and that gives us 6. That was a long one. That's the end of the lesson.